Okay, well, thank you, everyone. It's my pleasure to give this talk. I actually enjoy talking about physics and philosophy. Comparative religion was another hobby of mine. And I was also almost a classics major. And so if you guys ever want to talk about anything at all, please track me down. But I called this talk Physics, Religion, and Philosophy because I wanted a nice broad title, but then I figured give it a subtitle, or, well, that all depends on what you mean by God. And if any of you are in my physics class, you know that I do like to define the terms that we use, and that's from my philosophy major days. There's a lot of different conceptions of God out there. And this is just from the table of contents from Wikipedia when I put in conceptions of God. So there's the old Hellenistic ideas. There's the God of Abraham from Judaism, Christianity, Islam. There's the more Eastern religions, which have some similarities but a different source in their history. And then there's more modern and new religious movements. Things like the Baha'i faith are pretty interesting. Extraterrestrial conceptions of the divine. You can research that even on the History Channel these days. And more modern philosophy. So I just wanted to put this list up there because there's just so many different ways of thinking about God. It's important to really make sure who you're talking with knows what you mean when you use that word. Because of the work that I do over the years, people have asked me, Mr. Sanford, or in years before, like, hey, Bill, do you believe in God? You teach physics? And so I always start with, well, that all depends on what you mean when you use the word God. And so God can be sort of the God of Abraham. And I like that picture because it has the alpha and omega on it. And in physics, we use so many different letters, we had to move to the Greek alphabet. And so we actually use alpha and omega to talk about particular things. And it's the God of Abraham, the sort of personal, creative God, the God that has a personal interest in us and created the world, that I'm going to focus on a little bit towards the end. All right, and so returning to what I said at the beginning, accuracy versus precision. It's important in physics to be accurate and also precise, because otherwise, if you're very precise but not accurate, that's a picture from the cover of an old textbook on error analysis. And so that's a train that went a little too far and actually went out the other side of the train station. So that's a crashing train. And so they could have been as precise as they wanted, and they would have known exactly where, they would have known exactly how wrong they were. But if you're not accurate, then it doesn't really matter. It's important in philosophy to be accurate and precise because it may have certain moral consequences. That's a painting of the final trial of Socrates. And because he was very precise by saying, as a citizen of Athens, he would follow their laws to the letter. He actually drank the hemlock and killed himself because that was the verdict of the jury. And so it also can be important in religion to be accurate and precise. Let's see if we can hear this. Can we hear that? Anyway, this is the classic opening scene from The Life of Brian, where the three wise men, the three astronomers, they show up because they follow the Star of David, the Star of Bethlehem, and they go to the wrong manger. They go to the manger next door to the one that Jesus was born in. So they have this fun little encounter with Brian's parents. And so it's important to be accurate, because otherwise you might end up in the wrong manger. Okay, so why bother? Being precise with our meaning can avoid antagonism and conflict. And this is the main reason why I bring it up, is because oftentimes people would come up to me with a particular mindset and try to catch me in some sort of contradiction, saying, well, how can you be a physicist and believe in God? You must be an atheist. And so I would always answer, well, it depends on what you mean by the word God. And oftentimes somebody would say, well, I kind of think it's sort of the sum total of all the creation in the universe. And, I can get behind something like that. And so you can avoid a lot of argument if you're very precise and if you know exactly what other people are saying. And in philosophy, that's very important. In physics, that's also very important because we use a lot of words that we use in everyday life. Like something like the term work has a very specific meaning in physics. And even in something like psychology. The word depression, we have a very colloquial use for it. I'm feeling depressed today. But in psychiatry, there's a very specific meaning. And so if you're talking with a psychiatrist and you use that word and you just mean you're kind of feeling glum, they may send you to the pharmacy when you don't need to go. And being accurate can also be helpful. But again, it depends on what your goals are. Being accurate, if you're just trying to make yourself feel better, doesn't necessarily need to be as important because people can prefer illusion to despair. Okay, so this person you might recognize. His name is Albert Einstein. And this is my favorite quote of his and one of my favorite quotes of all time. And it's the most incomprehensible thing about the universe is that it's comprehensible. And so I really like this because it really encapsulates what we try to do in physics. And so, for example, quantum mechanics. What is a quantum? Quantum is basically a little discrete packet. It's sort of distinguished from our general ideas of a continuous reality. Quantum are basically little bits of physical quantities. Energy is quantized. That means something can only have a particular energy. And it's even more fundamental than that. In quantum mechanics, and later it's extrapolated to even space and time. Space in that length can only have discrete values. There's only a certain, albeit very small, short length that has physical meaning. There's only a certain length of time, albeit very short, that has a physical significance. We call that Planck length, Planck time. And if you ask if something is quicker than that very short, discrete amount of time, it's actually not a physically meaningful question. Okay, so then there's also this idea of the uncertainty principle, which means because of this discrete nature, we can't ever know with infinite precision where something is and what it's doing at the same instance. And so you can either know how fast something's going, but not really know where it is. And so that's where this wave-particle duality comes in. So it depends on the type of question you're asking. And there's lots of different experiments. One of the most famous is called the Stern-Gerlach experiment, basically where you shoot a beam of electrons at a series of slits, and the electrons actually interfere with each other, and you get an interference wave pattern on the other side, which shows that they act like waves, until you actually look to see which slits the electrons are going through. And as soon as you look, they somehow mystically pick a side to go on, and then you just get a single target hit on the other side as if it was, in fact, particles going through. And so that's sort of a little weird. And the Copenhagen interpretation of quantum mechanics tells it like this, that in quantum mechanics, you have something called the Schrodinger equation, but basically what it is, it's a probabilistic waveform of where in space and time you are most probable to be based on certain circumstances. And that until you make a measurement, that system exists in the superposition of all possible waveforms until something measures it. So basically, if you have that cat in the box and you don't know if it's dead or alive, according to the guys at Copenhagen, that cat is in a superposition state of being both dead and alive until you open the box and look, which is a little weird. But as it turns out, the universe really works that way. Transistors wouldn't work without quantum mechanics, and a lot of these effects. Cell phones wouldn't work, GPS wouldn't work, and so we know the universe works this way. It just doesn't make common sense, and that's because our brains are not wired to think that way. And another interpretation is something called decoherence, and that basically means that you can have these weird sort of superpositions of all possible states, but it's not that by looking you magically make the universe pick what's going on. This quantum state actually leaks information into the environment because the universe is so complicated. Just by being part of the bigger system of the universe, information about what's going on sort of leaks out, and that's why at our sort of bigger scale of everyday life, I don't accidentally walk through the wall by accident. I don't appear in two places at once, which does happen on the quantum level. And another interpretation is the many worlds interpretation, which you may have heard of, and that's for every moment that there is a possible difference in outcome, that instead of picking one or the other, the universe actually splits off into parallel universes, where in each universe that different outcome is manifest. And this has actually become, believe it or not, the most widely accepted because it's the most elegant in terms of the mathematics, and people have gotten a lot more comfortable with the idea of parallel universes. Okay? There's lots of different kinds of multiple universes out there. Okay. So, yeah, pretty comprehensible, right? Well, maybe. And so what we do is we use physics to try to understand what's going on. And so physics is this very elegant combination of math and nature. So we use mathematical models to make predictions. And so when you remember back to the scientific method, in order to have a scientific theory, we need to make some sort of falsifiable prediction that we can test by experiment. That means nature is our ultimate arbiter of what is actually going on. However, and this gets back to what Einstein said, this almost works too well. And there's no real known reason why we can use mathematics to model nature so well. But we can, and it works great. Planes fly, cell phones work. We can toss balls across the room and accurately predict every single time where it's going to land. So even though we don't understand why mathematics is the language of nature, it is. And in physics class, we start off talking about the physics of everyday life, throwing balls across the room, shooting projectiles off a cliff, and other projectiles which can go into orbit. And we do that because we start off that way so we can establish this almost mystical relationship between mathematics and nature. The fact that we can use math to build these models, just using equations and mathematical models that make a prediction, and when we go to look out in nature, it works every time. And the reason we start with everyday life is because what mathematics lets us do, it lets us go into those realms where common sense doesn't work, into those realms where our experience does not help us, into areas such as magnetism, and then even more so quantum mechanics, then later string theory, M-brain theory, where you can talk about supersymmetry in higher spatial dimensions, spontaneous symmetry breaking, and all kinds of crazy stuff, which doesn't really make a lot of sense. We can't even picture it in our head, because we were only designed to think of things in sort of three-dimensional space. But using the math, we can do certain calculations, which will make a prediction that can lead us into new areas, and we can rely on it. We, in a sense, have faith that the math knows the universe better than we do. And so the prime first example of this is Isaac Newton. he had the insight to use mathematics as the foundation of his universal laws of motion and gravity. This is a great book. It's called the Principia Mathematica. In this book, he basically lays out his theory of universal gravitation, and then along the way, he also invents calculus to verify some of his claims. It's a great book. I read it in its original Latin. It's got amazing diagrams because he couldn't use a lot of the more simple methods that we use for proving his statements. And so there's just diagram after diagram of these elaborate geometrical proofs that go all the way back to the ancient Greeks. So it's actually a very interesting read. And so he had this idea of this deterministic clockwork universe where once things get set in motion, things sort of unfold in a very predictable and certain way. And according to Newtonian mechanics, if you know the state of everything in the universe, where it is and where it's going, then you know what everything in the universe is going to do until the end of time and all the way back until the beginning of time. And Newton, he was actually a reverend in the Church of England. He said, and Newton was very comfortable coming up with these great ideas and not necessarily needing to explain the whole story. He said, my methodology works. The world works this way. Why is it so? Well, obviously, God set up this elaborate mechanical universe and set it in motion, and here we are. Newton was comfortable with that. And so the clockwork universe is deterministic, it's elegant, it's very appealing. It was the standard for many, many years. Unfortunately, it's not our universe. Well, what do I mean by our universe? Well, I mean the universe that we're in. And there is a great possibility of other universes out there. And again, getting back to quantum mechanics, if you think about this sort of meta space of possibility, superposition of all possible universes that are at all possible, sort of coexisting, but not manifest. Why is it our universe that we're experiencing? And there's something called fine-tuning, which might have been in some of the stuff that you read. The universe is very finely tuned to allow life to exist in it. And if certain things like the strength of electromagnetism and gravity were just a little bit off, planets wouldn't form, the periodic table would have just two uninteresting elements. If we had a very different number of extended spatial dimensions, things would just, you couldn't have carbon, you couldn't have complex animal life, you couldn't even have stars form, fusion wouldn't happen. And so it's very interesting that the universe is particularly the way it is. And people talk about something called the anthropic principle, which is, there's two versions. The weak one is that, well, if we have all these possible universes out there, of course it makes sense that we find ourselves in the universe that is possible for life to exist in. I mean, we wouldn't be here looking at a universe that we couldn't live in. And then the stronger version is that the universe has to be this way because the universe is designed for life. Okay, multiverse. This is sort of a general term to talk about parallel universes, multiple dimensions. This particular graph is from an article from Scientific American that a friend of mine from MIT wrote a few years ago. His name's Max Tegmark. He's a great guy and a great resource. And so there's different kinds, different levels of multiple universes. There is a sort of basic version where there could be other regions in our universe where we just can't see because the light can only go so fast. So we can't ever really know about those. And then there's something called inflation, which has to do with how after the Big Bang, the universe sort of rapidly expanded, spread itself out, so is uniform in all directions, with the exception of quantum variations. And people were like, why is that the case? And so a guy named Alan Guth came up with the concept of inflation. And so you can have other little regions, other bubbles of space-time that had different kind of inflation. So the laws of physics are basically the same, except little things might be different. Certain fundamental constants might be a little off. And then we have the many worlds, different universes where we have all these parallel coexisting universes where every consequence is manifest in a different way depending on particular outcomes. So say there's a universe out there where coin flips are opposite of what they are here. You can imagine that could be a very different universe for people here on Earth. And then finally, there is this level 4 set of different universes where things are just completely different. And these are those other universes where life couldn't even exist. Space and time is incredibly curved. You have extensions in space and time at higher dimensions that make it impossible for life like us to exist. Not our comfortable three-dimensional universe with an up and down, left and right, and back and forth. Okay. Now this little picture is called the Penrose triangle, and people have different interpretations of how relevant it is. I just thought it was an interesting thing. And so basically, there's different schools of thought about physics. And one is that physics can only explain part of our reality. And so it can explain why elevators work, and it can explain a lot of things. But physics can't explain things like human consciousness. Physics can't you can't explain the capacity for faith that human beings have in terms of physics and formula. And then there's another school of thought that says you can explain all aspects of reality in terms of physics. We just don't know all the physics yet. And this particular school of thought gets more and more adherence every day as more and more new physics is discovered. 200 years ago, people, it was harder to believe that you could explain everything in terms of physics. But now that we have a greater understanding of the relationship between physics and neurology and how it seems that the observer has such an intertwined coupling with the physical universe, that maybe you can talk about all things in physics and all things in the human experience in terms of each other. Maybe subjectivity can be explained in terms of math. And then there's this third form, which it probably represents my opinion the closest. And this is sort of, if that first one is sort of more secular, the second one is more fundamentalist. This third one is the more mystic one, where physics can lead us up to new insights, where it can show us patterns, and it can bring us to a place where we can then get this new understanding that transcends physics and subjectivity, and is something new emerges. Okay, so what about God? All right, is God possible? I remember when I was a philosophy major in school, I wrote a thesis paper called On the Temporal Nature of God. And because I was young and very sure of myself, I basically went about proving that the God of Abraham could not exist, that any God that exists in time, any God that has thoughts, can't create a universe, because thoughts exist within time. Time is part of the universe. And how can something create something that it is completely a part of? I got a 4.1 out of 4.0 on that one. However, many years later, as I learned more and more physics, I found that I should really go back and write an addendum to that one. Because there's certain ideas such as the bootstrap universe, there's the sort of intertwining the human experience in all this, that it may quite be possible to create the universe that you are part of. And so if human beings can get tangled up in that, why not something like God? Is God necessary? Well, I think that's for everybody to decide on for themselves. Okay? And so there was this idea of God of the gaps, where this is the God that inhabits the sneaky little places that human ingenuity hasn't gotten to yet. And that's sort of a somewhat diminishing role for God. And I'm sure if God exists, it's in such a way that he wouldn't be so diminished. I think God is either so transcendent that we are still trying to comprehend what he is, as opposed to some shrinking violet hiding in the corners. Okay, so faith versus reason. This is sort of where physics and religion come together. So is faith possible? I think so. Is faith necessary? I also think so. I think faith, and again, to be more precise by what I mean, I think of faith as the capacity of human beings to believe something without evidence. Okay? To come to a conclusion knowing that it may not be true. And I think, even from an evolutionary point of view, I think the capacity for faith has gotten humanity out of problems that, if we didn't have that capacity, we would have gone out like a candle. I think faith is the wellspring of all human curiosity. Because if you didn't believe that there was something else out there, even though you didn't know any better, you would never have left the confines of, say, your village or your boarding school, etc. Okay, and is religion necessary? I think that's more of a debatable point. I think religion can be very useful in organizing society, and it has had a great role as the initiative for morality for human beings. I think morality is important. I think faith is important. People have been moving away from religion, and actually at MIT in about 2 years ago, they founded the Institute of, what is it? I think it's Ethics and Transformative Values. Basically, the Dalai Lama showed up. They had this new center, and his idea was that, is there a scientific basis for morality out there? Is there a secular foundation that we can build morality on, so that human beings can be good to each other and have a reason they can believe in, even if they don't believe in religion? And the Dalai Lama said, I don't know what that is. That's why we're doing this research. So I thought that was very interesting. Okay. So my opinions. Okay, so there's a lot to be said, and I don't want to go on and on, but I do think about this stuff a lot. And so if you were to go to my Facebook page and look at what my religion is, it would say sun worshiper. And the reason for that is that many years ago, I thought to myself, well, as a scientist, I must always maintain a certain amount of empirical doubt. What is the one thing I can allow myself to believe, and really believe, knowing that it may not be true? And I thought about this for a long time, and I realized that what that is that I can allow myself to believe, despite the real possibility of some celestial calamity, that the sun will come up tomorrow, like the old song says. Okay? And actually gave me a lot of, it brought me a lot of sort of balance and peace. I mean, every sunrise is a reminder that despite any chaos that might be in my life, there's still harmony out there in the universe. I mean, the Egyptians, that was basically their scheme for thousands of years. But that's just for me. I think being able to have faith in something is what's important. And I think the capacity for faith is what makes human beings so special and so unique and so necessary for preserving for the long term. And so over the years, I've come up with these grander thoughts. And so these are some notes that my sister took when I was rambling on, not unlike right now. And basically talking about the possibility of the human influence on the nature of our own reality. And I'll just briefly touch on it so we can have time for questions. But basically, the idea is that in our model of physics, which we presume the universe follows, there are certain symmetries. One of the most basic ones is matter and antimatter. And when matter and antimatter come together, they sort of cancel out. And my favorite analogy is like when you add 1 and minus 1 together, you get 0, right? And you can think, again, of this superposition of all possible universes as this effervescent extension into reality around sort of a 0 energy level. So basically, you can think of maybe a 1 and a minus 1 on the number line coming into existence and then canceling out. But in terms of a physical reality, the same thing can happen. They call these virtual particles. They happen all the time. We've measured them. Particles come in and out of existence, and they cancel themselves out. So you can think of universes doing the same thing. And so you can think of all these different universes coming in and out of existence, but always canceling themselves out. It's always a zero-sum game. And mathematics very much, in that sense, is a zero-sum game. It can't hold together on itself. And Gödel has some things to say about that, his incompleteness theorems. So why does our universe have this physical reality? We can look out there, and there is something there. And I remember I saw this talk years ago where the presenter was talking about new data from some new experiment where they discovered a tiny little difference between matter and antimatter. And so essentially that in the case of the universe, unlike the math we use to model it, 1 and minus 1 don't quite cancel out. And so it occurred to me while I was watching this, and I started to sweat and get all excited, that maybe by the act of trying to really nail down that difference between matter and antimatter, we actually define it from the point of view of the universe from which we're making that observation. And so the reason why there is this particular universe is because we were here mucking around with our high energy physics experiments, and we happened to accidentally break a symmetry. And so the universe sort of cascaded around that one sort of linchpin. And so if humanity can sort of be involved, I think there's many other possibilities. And so I'll leave it there. And if you want to ask questions, feel free to. And so this video is from NASA. This is the Wilkinson microwave anisotropy probe. So basically, this shows all the universe sort of collapsing from variations from its initial quantum state. So if you remember that beginning picture of those little different colors, that robin egg, those are just tiny variations in temperature and matter density. And those are from quantum fluctuations. And so when the universe first comes into existence, when you get this expansion into physical space, all those vanishingly small variations in space and time are what seed the higher structure of the universe. All the galaxies and all the greater voids and higher structure of matter in the universe get their origins at the very smallest level, which are quantum fluctuations that happened after that spontaneous symmetry breaking at the beginning of our universe. Okay, and so as in most things, my ideas are heavily influenced by people who have come before me. Most specifically, Thales, who is a very old natural philosopher from the time of the ancient Greeks. Look him up, he's great. Galileo, Newton, Einstein, of course, Hawking, Penrose, Richard Feynman. John Wheeler, he's one if you're interested in this idea of how consciousness and the manifestation of the physical world interplay. He's a great resource for that. And Max Tegmark, he's a very good friend. We work together at MIT, but even more so, he's one of these people, if you watch these shows on the Discovery Channel, on PBS, he's one of these guys you'll see. So you'll recognize his name. He's a very kind-hearted person, and he's very much interested in all this stuff. And so his website at MIT is a good resource, so I'll just throw that up there. And he's got different articles he's written, links to other things. Okay, so why don't we pause here, and I'll take some questions, and I'll answer as many as we have time for. So any questions? Okay, yep.
Do you believe God is the reason the universe is so fine-tuned?
Do I believe that God is the universe, that the universe is so fine-tuned? I don't know. He certainly could be. And again, it depends on what you mean by God. It's certainly a possibility that I am not willing to discount. But I really can't say. I don't have enough information. Any other questions? Yeah.
Do you think there's anything that drives the quantum states that different particles will go through, like the random movements or fluctuations? Do you think there's anything that drives that?
Yeah. So it's actually not completely random. There are certain probability distributions in different sort of mathematical phase spaces, probability space. And so there's usually a distribution around most likely outcome that sort of tapers off, but never quite gets to zero. So there's usually a vanishingly small possibility of very unlikely things happening, but there is sort of a weighted average of likely outcome. So did you have a question?
Yeah,
Do I actually what?
do you actually think multiverses exist?
I think certainly some of them do. I think in terms of physical realities that we don't have access to, that's probably true. In terms of the multitude of universes that sort of come into existence with every possibility, I don't know, maybe. And this is one of those hard things, because now we're sort of getting a little bit beyond physics into metaphysics, because physics, you need to have an experiment that you can test it. And so people are trying very hard to come up with experiments of how we can detect the effects of these sort of other universes out there. And so some people have made some progress about that. So stay tuned. Okay, anybody else? Yeah.
So if there are multiple universes, how do we know we're not all in a giant dream, we're all in the Matrix? How do we know that?
Okay, so in philosophy, there's a term for that. It's called the veil of ideas. And that's, can we ever really know anything beyond our own sense impressions? Because we know that we're having a certain experience, but how do we know we're not just caught up in some fevered dream? And some people might make the argument that, is that really a meaningful distinction? But some people are uncomfortable with that idea. And so that's something that you really have to come to decide on your own. When you're a philosophy major, you sort of adopt all the philosophies of the people you're studying at the time. And then after 4 years, you can kind of see where you stand. And so for a while, I was worried about that. And of course, right when I was reading about that kind of stuff is when The Matrix first came out. And so that movie is the bane of philosophy majors everywhere. And yeah, no, it's hard. And then there's another sort of related idea called the holographic principle. And that's because the universe is made up of these discrete quantities, these quanta, that perhaps our universe that we experience is really a holographic projection of some higher dimensional space. And so that we could be some computer program or some other sort of algorithmic expression of a higher dimensional code, as it were. And people made the argument that because in quantum mechanics, things don't seem to really decide what they're doing with themselves until you look. They say, well, if you think about a graphics rendering engine on the computer, it doesn't draw what your little AI character isn't looking at until you turn them around, and then it quickly draws what's over there. And the universe kind of works a little bit the same way. And so some people think, all right, well, maybe our physical universe is this holographic projection. So we're basically all the information in our universe can be contained in some other set of equations in a different set of dimensions. And so that might be true. Some people believe that. Okay, any other questions? All right, well here, I'm just going to wrap it up with one thing. When you're a physics major and a philosophy major, you also dabble in other things. So here's a little poem that I wrote. It's called Unfinished. And I like this one because it has a lot to do with all this stuff. And I wrote this more than 10 years ago. Okay? And so it starts off, I am a player of games. I think and I drink and I blink and I turn the world around. I am a collector of things. I learn and I forget and I believe. And I think I know what red is. Yesterday seems to have happened. I walk upstairs and turn doorknobs. Also, I see triangles in my mind. I have designer thoughts, though I try to clear my head. I distinguish between love and water. I excel in standardized exams. I can't seem to get above myself, even though I got an A in geometry. I look at my watch sometimes, and then that's it. I ran out of poetry, and I think we ran out of time, so thank you. Thank you very much.